So today we will be looking at enzymes. This is our last little section of the chapter in proteins. We said that proteins are very, very special molecules, and they have very many different functions, and one of those many functions is of enzymatic catalysis. So we're taking a look at this specific function of proteins. So enzymes are proteins. Everything we've said about proteins, we've said that they are composed of amino acids. So amino acids are the building blocks of proteins. Therefore, amino acids are the building blocks of enzymes. We said that proteins have a very intimate relationship between their structure and their function. Same thing with enzymes. Proteins have a primary, secondary, tertiary, and sometimes even a quaternary structure. Same thing for enzymes. So anything that I'm saying today about enzymes, just think of everything we had already mentioned for proteins. It's still in place. Okay, so enzymes will have a primary structure, which will be the sequence of amino acids. Enzymes will have a secondary structure. And what's the secondary structure held by? What kind of bonding? The primary structure is peptide bonding. The secondary structure is? The secondary structures are alpha helix and beta pleated, and they're held together by what kind of bonding? Hydrogen bonding. Okay, so the primary structure is peptide bonding. The secondary structure is hydrogen bonding. What about when these alpha helical structures curl even more and they give a tertiary structure? This very intricate, raveled structure. What are those forces that keeps that tertiary structure in place? Disulfide linkages is one. Very good. What else? Hydrophobic interactions. That's very good. What else? Salt bridges or ionic interactions. Very good. And more hydrogen bondings. Okay, so all these forces will keep a protein in its tertiary structure, and the same thing for enzymes. So enzymes are very complex molecules, and their function is a very important one. Their function of enzymes is to what? They catalyze chemical reactions. So in our body, many chemical reactions are taking place right this second as we speak. And all these reactions take place very, very fast because of this biological catalyst that we have that function at body temperature under many different pH ranges. And the very first thing we're going to look at is how do molecules like enzymes work? What is the magic behind it? Okay, so in order for us to understand that, I'm going to show you an energy diagram of a chemical reaction, any chemical reaction. So I have on the screen an energy diagram of a reaction between hydrogen and iodine to forming hydrogen iodide. Any chemical reaction. Any chemical reaction that we've studied, and we've studied many different chemical reactions in this course. You have, before the arrow, your reactants. So these are your reactants. And these hydrogen molecules and iodine molecules will collide. So in order for them to collide, energy has to be given. Okay, so if you have a hydrogen, H, and an iodine, I, and this molecule is flying up and this molecule is flying down, this bond needs to break, that bond needs to break, and a new bond needs to form between the hydrogen and the iodine. Okay, so any molecule that appears before the arrow is called a reactant. In this chapter now we're going to call it a substrate, but it really means reactants. So substrates and reactants mean the same thing. And these substrates or these reactants have to have enough energy in order to break some bonds and form some new bonds before products appear. Okay, so in this simple reaction, hydrogen and iodine are colliding, and the bond between the two H's and the two I's is breaking, and a new bond between H and I is forming. So energy is a super important factor in order for a chemical reaction to take place. The energy that's needed in order for reactants to end up as products is called the activation energy. Okay, so it's like a energy barrier. You have to climb up this hill of energy. This is an axis where energy is plotted, and once you have that much energy among the collisions of your reactants, then your products may appear. If you don't have enough energy, then your reactants will begin to climb the energy barrier and come back down, and nothing happens. No products will appear. But if you do have enough energy, and this could be measured in kilocalories, in kilojoules, then your products will appear. Okay, so I have a reaction, a simple reaction giving you products because this energy of activation is met. Okay, a simple analogy would be, let's say we want to go to Italy. Well, in order for us to go to Italy, there's a little barrier. We need to have money. Okay, so if we have enough money, like this study abroad is like $3,000, around there. So if you have $3,000, which is your barrier, you can make it from Miami to Italy. If you don't have $3,000, you can go to Hialeah and back. Okay, so there are barriers in order for circumstances to take place. I am specifically addressing about a chemical reaction, and the term activation energy is the barrier that I'm talking about. So how do enzymes work? If this is a reaction between, let's say, maltose, and maltose is going to break down to form what? What is maltose? Two glucoses, glucose and glucose. That is going to take place. You have to break a 1,4 glycosidic bondage. Okay, so we've talked about many, many different chemical reactions. If that reaction has an enzyme that speeds it up, then it can take place so much faster. So what's happening is there's an energy barrier, and maltose would end up as two glucoses if that energy of activation is present. But the enzymes are these marvelous little, not little, marvelous large macromolecules that find a shortcut. It's like, you know what, maltose, instead of going through all that huge barrier, there's another way to go. And this is your new energy of activation. You start from the energy of maltose, and instead of having to go all the way to the tippy top of that hill, you can maybe cut that in half. Okay? So you still get two glucoses, but you find a shortcut. So the energy of activation value, I'm calling it energy of activation prime, as opposed to the normal energy of activation that would exist without the enzyme. Okay? So enzymes find a shortcut. They go from the exact same reactants, and now we're calling those substrate, and they go to the exact same products, but they find a shortcut. The enzyme makes products appear very, very fast. And what they're doing is it's like you find a tunnel to go from one side of the mountain to the other side of the mountain. So instead of having to climb all the way to the tippy top of Mount Everest, you found a tunnel and you go to the other side. Okay, so this is how enzymes work. Enzymes that would catalyze the hydrolysis of maltose are very specific for maltose. The name of the enzyme that catalyzes this reaction is maltase. So maltase catalyzes the hydrolysis of maltose, only maltose. If you want to hydrolyze lactose, then you need to use what? Lactase. Okay, so lactase doesn't work on maltose. Lactase only works on lactose. If you want to hydrolyze sucrose, what's the enzyme? Sucrase. So the ASE ending for us means we have an enzyme operative. And this enzyme will find a shortcut, will take your substrates through another pathway to make it to products so much faster, millions of times faster. How do they work? There are many mechanisms that have been proposed to understand the action of enzymes, and the lock and key mechanism is the one that I would like to refer. The lock and key mechanism for enzyme action. Okay, so this is the mechanism of enzyme activity, enzyme action. And it explains this diagram in a very simplistic way. You have your substrate, which could be maltose or lactase or sucrose or whatever substrate it may be. And there's an enzyme, a very large protein with its primary, secondary, tertiary structure that's going to catalyze its reaction. The enzyme is going to have a specific place called the active site. Let me just make this a little bigger. The active site, which is a pocket where your substrate has a perfect fit. Just like if you have a right glove, you are going to have your right hand to fit it in. The left hand's not going to fit in there, but the right one will. When the substrate finds its enzyme and approaches, goes down into the active site, into that pocket, then the substrate is held in place, and whatever reaction needs to take place, in this case, breaking a 1,4 glycosidic linkage, will take place. Okay? So that reaction occurs at the active site, and you no longer have maltose, now you have glucose and glucose, but they're still inside that pocket. And once that reaction takes place, then the two products, which would be glucose and glucose or whatever, if this is a different reaction, it will be different products, will appear. And the beauty is that the enzyme is totally recyclable. That enzyme goes back and grabs another maltose and keeps catalyzing the reaction again and again and again, faster and faster and faster than it would be taking place without it. Okay, so the lock and key mechanism is one of many mechanisms that try to explain the mechanism of enzyme activity. Okay, so the active site is, what is it? The active site is in the enzyme, and what is it? It's the place where, the pocket where the substrate fits just perfectly. Okay? Now we can begin to understand why D versus L saccharides can be digested or not. Why cellulose is not digested, because those beta 1,4 glycosidic bonds are pointing totally different, and they will never fit in an active site of the enzyme. Okay, so you first have an enzyme reacting with a substrate. So that's step one. Step one, you have your enzyme reacting with your substrate, and you form a complex enzyme substrate. Then this concept, complex enzyme substrate, breaks down into what? Enzyme product. And it's still, thank you, it's still a, did everybody sign? It's still a complex. They're still tied together. And once this complex enzyme product is formed, then the enzyme is free and your products are visible. Okay, and that enzyme goes back and does the same thing again and again and again. Okay, so these are the 3 steps, simple steps, that will explain the mechanism of enzyme action. Okay. So if I have an enzyme that is going to catalyze the hydrolysis of a lipid, what would that enzyme be? Enzyme, I'm sorry, what did you say? Right. So a lipase will catalyze the hydrolysis of a lipid. A hydrolase, what would a hydrolase do? A hydrolysis reaction. Okay, so maybe you're hydrolyzing maltose, and you're talking about maltase. Maybe you're hydrolyzing lactose. Maybe you're hydrolyzing sucrose. So a hydrolase catalyzes a hydrolysis reaction. Hydro means water, lysis means breaking. A isomerase would catalyze an isomerization reaction. So maybe fructose can turn into glucose, moving that carbonyl from carbon 2 to carbon 1, and an isomerase will do that. Goes from one isomer to another. Sucrose and glucose are isomers, right? We know that. Ligases are also called synthesases, join 2 or more molecules together. Okay, so the name ending in ASE indicates that we have an enzyme, and these enzymes have hundreds of different functions, depending on what reaction they are catalyzing. Okay, so I just gave you a few examples of these. Some enzymes are labeled as simple enzymes. Some enzymes are not so simple, and they're labeled conjugated. What do we mean by a simple enzyme or a conjugated enzyme? Well, the difference, anybody knows the difference between a simple versus a conjugated one? A simple enzyme? No, every enzyme is one. Every enzyme is just one enzyme with its primary, secondary, tertiary, a big, huge macromolecule with all these alpha helical sections and... I'm sorry? Something about a vitamin, yes. What's the something? If besides the protein, if besides the 259 amino acids that you have in its primary, secondary, and tertiary structure, you have something else like a vitamin or a metal ion, like hemoglobin has iron plus 2, we had said. Hemoglobin without iron plus 2 won't work. Well, some other enzymes require other metal ions. That means that besides the protein, you need either a vitamin or a metal ion to work. And these are called a cofactor. So protein plus a cofactor gives you a conjugated enzyme, as opposed to a simple enzyme. And again, by the way, when I say simple, it's totally relative. Simple compounds were 15 weeks ago, and we talked about water, H2O. That's very simple. There's really nothing simple about an enzyme, because you have molecular weights of hundreds of thousands. But by simple, I mean it's just the protein. All it has is a lot of amino acids linked together by peptide bonds, curling in alpha helical structures, forming globular proteins. But if that's all you have, that's called a simple enzyme. Okay, so a simple enzyme consists of only a series of amino acids. And it could be as many as 50 amino acids. We said insulin was a protein and it had 51 amino acids. Okay, so if that's all there is, only a series of amino acids, that's a simple enzyme. But if you have a conjugated enzyme, besides the protein, you need a vitamin, or you need a metal ion, you need something else, you need a cofactor. Okay, so that's some. Okay, let's look at problem 7. Classify the following enzymes as simple or conjugated. 7a. Pyruvate kinase requires magnesium plus 2 for its biological activity. What do you think? It's conjugated, okay? What about 7d? This enzyme is composed of 250 amino acids. And that's going to be a simple one. And again, simple is a totally relative. There's nothing simple about 250 amino acids linked together with all these hydrogen bonds and all these disulfide linkages and all these ionic bonds. But that's what it takes. That's what it takes, the 250, in order for that reaction to be catalyzed. E. This enzyme contains a carbohydrate portion. That's conjugated. Okay, a carbohydrate is not an amino acid. By now we know what carbohydrates are, right? Glucose, maltose, those are carbohydrates. Amino acids are not carbohydrates. Carbohydrates are not amino acids. So if you need something besides your series of amino acids, then you're needing a cofactor for it to work. So that's a conjugated. Okay? Are we okay? Move on. Okay, let's look at some factors that affect enzyme activity. Factors affecting the catalytic action of an enzyme. The activity of enzymes. Can anybody tell me what some of these factors are? What would be one? What do you think? I'm sorry? What did you say? I'm sorry? Substrate concentration. Yes. So if I'm doing a study of an enzymatic catalytic activity in vitro, I'm in the lab and I'm trying to understand what does this enzyme do and how does it do it. Okay, these enzymes have tremendous applications in medicine especially. If I am doing this with test tubes in vitro and I have X number of molecules of my enzyme, the more substrate that I put in my test tube, the more products that I'm going to get. Okay, so the activity of the enzyme increases if I increase the substrate concentration. Okay, so I can make a plot, and if I do the activity of the enzyme versus the concentration of substrate, brackets means molarity, I am going to get more and more activity until all the enzymes used. So all the enzymes used, all the active sites have been taken, so then the activity plateaus. So a plot of enzyme activity of enzyme versus substrate concentration would look like this. It increases. If the substrate concentration increases, the activity of the enzyme increases up to a certain maximum where all the enzyme has been used. So if you don't have any more maltase around, I don't care how much maltose you put in that test tube, no more glucose is going to show up. Okay, so we measure the amount of products to realize what is the activity of the enzyme. Very good. What would be another factor besides enzyme concentration? How about enzyme concentration? What do you think that would do? If I have a test tube and I have maltose, the more maltase that I add in there, the more products I get, right? And that plot would look totally different if I have a plot of the activity of the enzyme, enzymatic activity, versus the concentration, brackets means molarity, of the enzyme. Okay, so I can prepare a solution of enzyme, and this could be 0.001 molar or whatever, I can have a certain concentration of it. The more enzyme I have, the greater the activity. The greater the activity, the greater, and this will go up forever. It will be a straight line, a linear dependency. Yeah, it will be more and more products, more and more. Okay, so, okay, what would be another factor besides substrate concentration or enzyme concentration? Temperature. Temperature is a very important one. What is the optimal temperature for an enzyme? Body temperature. So these enzymes are occurring right this second in your body. And your temperature is around 37 Celsius, 98.5 Fahrenheit. So temperature, what would happen if I'm doing an in vitro study and I change my temperature from 97 Fahrenheit to 200? What do you think is going to happen? My enzyme will die. Yeah. But we don't say die, we say what? Denature. Now you sound like you heard last lecture. Okay, yes, we're killing the poor enzyme, but we're really saying it in a different way. We denature we begin to unfold. Okay, so the tertiary structure, those ionic bonds that are keeping that intricate tertiary structure in place, or those disulfide linkages, or those ionic bonds, if you disrupt those, if you unfold that enzyme, you no longer have an active site. You no longer have a place where your substrate can fit. You no longer have products. You no longer have catalysis going on. So I'm sorry? When you get a fever, yes. Actually, fever is not bad. Fever is fine, but you're only increasing your temperature a few degrees. Somebody had asked that last time. Okay, so if you're increasing your body temperature from 98 to 99 to 100, your metabolism is faster. So the higher the temperature, the higher the activity up to a certain point. If you get to 105, you're going to go in an ice bath. Because if you don't do that, if you don't control your temperature, you die. That's lethal. Okay, so you have a little buffer region, but it's a very small region. You cannot jack it up 100 degrees because you don't survive. Okay, so we're talking about human beings here. We're studying this in vitro, and you may jack it up 98 degrees, 99, 100, and a rule of thumb is if you increase the temperature, the reactions proceed faster because you have higher and higher temperature, meaning thermal energy, and that thermal energy is going to translate to kinetic energy. Those molecules can collide and have that energy to make it to products through that energy barrier, the energy of activation. So you're going to get to products faster the higher the temperature you have, but in the case of enzymes, up to a certain point. Okay, so if you go up 20 degrees, you are in trouble. You are not going to tell the story. Yes.
So then that's why freezing slows down?
And freezing slows down. Exactly. It's when you lower the temperature, it's the same thing. The activity will decrease, and again, it's less kinetic energy, and you have no energy to climb that energy of activation. Okay, so if you have a lot of collisions, I don't care what reaction it is, maltase going to maltose, you can climb up that energy barrier and make it to products. And the lower the temperature, the lesser energy that you have, less collisions, and you go back to reactants and no products are formed. Very good. What other factor do you think? pH. Very good. So let's go back to factors. pH. How do you think pH will affect? Over the neutral. So you're assuming pH must be 7? Blood has a pH of 7.5. And we've talked about alkalosis, and so by now we can wrap up. We've learned a lot. This is one little compact course. And you have been addressing what happens when acidosis and alkalosis takes place. Okay, so That wasn't very good when we had acidosis and alkalosis. We faint, we die, we get sick. That's not exactly right. So the pH of blood has to be around 7.5, or else we faint, or else we die. but does it have to be 7? No. What about if you are looking at the reactions that take place in your stomach? I mean, we are an amazing laboratory, so efficient and so perfect. It's marvelous that we can eat all these huge meals. We just finished picking out in Thanksgiving. I know I did. And I didn't die from that. Somehow my stomach managed to digest my turkey and my stuffing and my desserts, and I had 2 crêpes Sucettes and whatever. And I didn't die from it. I almost felt like I did, but I didn't. So the pH in the stomach must be much harsher, much different than the pH of blood. Okay, the pH in my intestines is totally different. So if I'm talking about the reactions that occur in my stomach, then the pH is going to be around 1.5, because I'm going to need to hydrolyze this huge protein that I just ingested. Or if I'm talking, okay, so my pH could be 7 or 7.5 if I'm talking about blood, but maybe my pH is 1.5 if I'm talking about the reactions that take place in my stomach. Or if I'm going to my intestines, maybe my pH is 8, because now I'm going, sucrase needs to go down to sucrase goes down to, hydrolyzes sucrose and breaks it down to what? Glucose and fructose. We haven't forgotten anything, right? We know all our chemistry together. Okay, so depending on what section of your body you are contemplating, what reaction is taking place, okay, so the biological activity of enzymes begin the minute you put food products in your mouth. Okay, so salivary amylase begins to break down your carbohydrates. So if you had oatmeal for breakfast, the minute you put that oatmeal in your mouth, these very large polysaccharides are going to begin to be broken down, and the pH there is totally different than the pH that it's going to get to when it gets to the stomach, or when it gets to the intestines, or when it gets to the blood. Okay, so the pH is a super important factor. But what happens if I'm talking about my stomach enzymes and I no longer have a pH of 1.5? I change that pH in vitro. Okay, I'm not going to change the pH of a person in the stomach, but I'm studying this in vitro in the lab. I change the pH to 0 or the pH to 5. What do you think is going to happen to that enzyme? It's going to denature. Good. It died again. Okay, so it's going to unfold. It is no longer going to have the secondary structure, the tertiary structure that it needs to catalyze the reaction. So the pH is a very important variable that affects the activity of the enzyme, and enzymes have a very narrow pH range and a pretty narrow temperature range in order for them. They're very special, but they need to be taken care of. So take care of your body, because it's doing lots of things for you. Okay, and there's a maximum pH and an optimum pH. Okay, and the optimum pH depends on the enzyme. Optimum pH above or below. Okay, so if it's pH, you can go from 1.5 to 2 if you're talking about pepsin. Pepsin is in your stomach, and pepsin hydrolyzes your food products, specifically proteins. So now you're ingesting a steak or whatever it is, pork. Some people ingest all kinds of different proteins. Okay, and it's a very narrow range. But if it's sucrase in your intestines, then the pH is totally different. Okay? Any questions so far? We're good? Okay. Problem 8. Describe the effect of the following of the rate on the rate of the reaction that catalyzes sucrase in the small intestines, and it has an optimum pH of 6.2. Sorry, I have a wrong value for sucrase. 6.2. 6.2 at a temperature of 37. Okay, so you're imagining you're studying this in vitro, and you have sucrase in a test tube and sucrose in a test tube, and you're playing around. Okay, now we're going to have a pH of 6.2, and now we're not going to have a pH of 6.2, but we're going to sucrose 6.2 and a temperature of 37 Celsius. Let's say I'm going to change my temperature to 55. Okay, so I'm doing 8E. I change my temperature to 55 degrees. What do you think is going to happen? What's going to happen to the rate of the reaction? Meaning, is it going to increase or is it going to decrease? It's going to decrease. Why is it going to decrease? Because my temperature has been tremendously changed and my enzyme is denaturing. Okay? What happens if I decrease the temperature to 15 degrees? It's going to slow down the reaction. Okay, so I'm not going to see as many products, and if it's sucrase, I'm looking for how much glucose and fructose are in my test tube. So I have a way to monitor the appearance of products, a way to monitor the disappearance of reactants, sucrose, in order for me to measure the enzyme activity. 15 degrees was what? C. What about if I increase the pH to 8? Okay, so every unit of pH, the concentration and molarity is changing tenfold. Okay, remember a pH of 10 to the minus, the concentration of hydrogen ion of 10 to the minus 6 gave you a pH of 6, right? And 10 to the minus 6 is 0.00000012345. That's the molarity. That's equal to 10 to the minus 6. And if I'm going to a pH of 8, my concentration of hydrogen ion is what? 10 to the minus 8. Okay, so I'm decreasing it 100 times. I have 100 times less. Concentration. Okay, so if I'm increasing the pH, the concentration of hydrogen ion will decrease 100 times, and the activity will stop. You know, you're denaturing the protein and will decrease the activity.
So with denaturing, what is is why when you get such an acid, a really strong acid or really strong base, it'll burn you?
It will burn you. Yeah. Yeah. If you have, I get nitric acid in my hands all the time in the lab, and the skin gets yellow. All I did was denature my protein. And it's going to stay yellow until I grow new protein, until I grow new skin. Okay, so once you killed it, once you denatured it. But your body will repair itself. We are amazing. As long as we take care of ourselves with good diets, with exercise. Okay? Any other questions? Okay, one more little section here, enzyme inhibition. Why do you think this is even a topic? Why do we need to consider inhibition? Why would we, the word inhibition means to stop, right? Why would we want to stop an enzyme activity? Because of what? I'm sorry, what did you say? Enzyme inhibition means I want to stop an enzyme from working. Why would I do that? To stop what? Let me give you an example. My daughter, when she was little, she's no longer little, but when she was little, she had ear infections forever. You too. It's a very common thing. Every couple weeks, it seemed like we had to go back to the pediatrician, and she would get a little cold. She was very allergic. Her ears would get full of fluids, Bacteria will love that environment. Bacteria will thrive in that environment. Bacteria needs to grow and reproduce with their enzymes. Okay? And the more bacteria that would be in her little ear canal, the greater the pressure and the greater the pain. And Jenny would start screaming in the middle of the night, and as a baby, she would just hold her ears. Oh, and I know, okay, another ear infection. We'll go to the pediatrician, and what does the pediatrician do? Give her an antibiotic. What does the antibiotic do? It stops the growth of bacteria. Okay, so you can have a bacterial infection, and antibiotics, thank God, were discovered because some people studied enzymatic activity in vitro and discovered that things like penicillin, for example, would not allow bacteria to produce their cell membrane. And the bacteria cannot have cell membranes because it's stopping the lipids from happening. Those glycerophospholipids are being stopped from the production, and membranes are no longer part of bacteria. Bacteria dies. Okay, so the minute you stop the replication and the growth of bacteria, you are controlling the infection, and Jenny would start screaming. Okay, so this is a very important application in medicine for inhibition is. So a normal substrate will normally get to an enzyme and will have a perfect fit in, what is this cavity called? The active site. But if you trick the enzyme and you give them a medicine, like an antibiotic, like that has a structure very similar to the substrate, but maybe has an extra couple methyl groups in there. It's a different fellow. And that is going to fit in the active site. And you flooded with this inhibitor, with this antibiotic. Then the substrate, when it's going to go in there, it's already blocked. It's already taken. Okay, so the inhibitor approaches the active site, blocks the active site by occupying it, and no reaction takes place. The substrate never made it. So you stopped the reaction from happening. Are you with me? Exactly. So you give him the medicine grabs in that little pocket in that active site, blocks the pathway of the substrate. Substrate can no longer get there because it's taken.
What happens to the substrate?
The substrate remains a substrate. Okay, so if you don't farm your products, you're stopping that reaction from happening. And in that case, you need, so I'm talking about the production of glycerophospholipids. So you don't get any glycerophospholipids. And if you don't get any glycerophospholipids, cell membranes cannot be produced. And if cell membranes cannot be produced, you're killing bacteria. Okay, so if you stop any of the hundreds of reactions that are taking place in your biochemical reactions that are taking place in your body, you're stopping the whole process. Okay, so you're controlling the infection. Okay, and antibiotic controls infection. One thing that you do in vitro, what happens if I'm studying enzymatic inhibition in vitro, in the lab? I have this in a test tube. I'm not doing this with humans. And I have an inhibitor and concentration, and then I go ahead and increase the substrate concentration. I duplicate it, I triplicate it, I quadruplicate it. I put a lot more substrate in my test tube. What do you think is going to happen? I'm going to get my reaction to go. I'm going to reverse my inhibition. I wouldn't kill the bacteria. I would continue to form my products, and those are the products that the bacteria needs in order for it to survive. So I would reverse the inhibition by adding more substrate, by flooding my system with substrate. Okay, so statistically now I have gazillion, maybe more molecules of substrate, and they will make it to this active site. And the minute they make it into the active site, I will get a reaction. I will get my products to appear. Okay? As opposed to, this is called competitive inhibition. Why is it called competitive? What do you think? Competitive inhibition has the substrate and the inhibitor both competing for the same. It's like you're going to, I don't know, a shopping mall and there's so very few parking spaces. Black Friday, and there's a competition for a space. Okay, the space in this case is the active site. As opposed to non-competitive inhibition. Non-competitive inhibition is represented by this diagram. Let me see if the diagram is really worth 1,000 words or not. You have now a substrate, you have an enzyme, and you have an inhibitor that doesn't go for the active site, but it goes elsewhere. And remember, this is a protein with its primary, secondary, tertiary structure. If this binds elsewhere, you are unraveling that protein. You are changing that tertiary structure. You are changing the site, the active site. And what happens? The substrate doesn't fit in there anymore. So you're stopping a reaction from happening. No reaction takes place, but it's a totally different type of inhibition. Okay, so a non-competitive inhibition. It still inhibits the reaction. It still blocks the reaction from happening. You still have no reaction. But the way it does it is totally different. Inhibition. No, you want to block a reaction from happening. Like this, for example, if you have heavy metal poisoning, why does that kill you? Why? Well, you are stopping reactions from happening. Lead plus 2, mercury, these heavy metals bind to your enzyme, and by doing that, you're forming a new bond. And that's going to change the tertiary structure of your protein. That's going to denature your protein. And whatever substrate needs to fit in whatever little pocket is no longer going to fit because it no longer has the same shape. Okay, so heavy metal poisoning would be a non-competitive inhibition, and you are killing yourself. Yeah. I'm on page 270, by the way. Are you there? Competitive and non-competitive? Yes. I'm sorry?
With a non-competitive, since there's no shape for the substrate to go in, even if you have more of the substrate.
Perfect.
The non-competitive.
I don't know if you guys hear what she's saying. I'll repeat it. A minute ago, we talked about competitive inhibition, studying it in vitro, and in studying, I flooded the reaction with substrate and I reversed the inhibition. So she's going, okay, what happens if I'm doing the same thing? If I am studying this reaction in vitro and I go ahead and flood my system with substrate, am I going to reverse the inhibition? No. Very good point. So I am flooding and I put more and more of my substrate, but they don't fit. The active site no longer have the same three-dimensional structure, and that no longer will make a difference in my inhibition. I still stop. So that's how I can differentiate competitive versus non-competitive. I flood my system, and if I reverse the inhibition, it's competitive. If I flood my system with substrate and I do not reverse the inhibition, it's non-competitive. Got that? Everybody heard that? Yeah.
By adding the non-competitive inhibitor, it just like changes the shape.
The shape of the active site, of that pocket that the substrate needs to fit in.
Alright, so it doesn't fit and there's no reaction.
Right. And if it doesn't fit, there's no reaction.
And it's
You
always going to be like that?
substrate, yes, it's going to be like that.
So it just changes the shape instead of just fitting it in.
Exactly.
Okay.
Yes. Speak really loud.
Why is it that competitive? When you said when you raise the concentration of substrate,
It would reverse it? Okay, statistically. Right. Okay. He's saying, why can I reverse the inhibition. By reversing the inhibition, what am I saying? It's like a double negative. That's why it's confusing. Okay? The inhibition means you're inhibiting a reaction from happening. Okay, so you have a reactant going to a product. And if you're inhibiting it, you're blocking that reaction. That's an inhibition. The reactant doesn't go to product, it stays as reactant. So if this is a bacteria that needs to duplicate and replicate and grow, and you don't let that happen, you're stopping the bacterial growth and bacterial infection from happening. If it's competitive, and I am adding more and more substrate, then statistically, the substrate will make it to the active site faster than the inhibitor making it to the active site, because I'm flooding my system with substrate. So now, I'm reversing the inhibition. My substrate made it to my active site, and I'm getting products, because I have the same shape of my active site, and I have so many more substrate molecules in there. Does that make sense? Now, if it's a non-competitive, I can flood it with tons of these, but they're not going to fit in here because I changed this structure. Okay, so think of your right glove and your right hand. That's a fit. Now, if I change that glove and I give you a different glove, a little kid's glove, your right hand's not going to fit in there because my fit, this guy, is a totally different shape than what that is. So I can triple this, quadruple this, tenfold the concentration of substrate. It's not going to fit.
I guess the reason I ask is because the way I see it is I feel like they're both competing.
Mm-hmm.
But if
Yeah,
it's
like
saturated,
adjacent.
then I would see that they could always get there before the other one.
If they could both come in.
No, because this guy's going to get in there. I have regardless, you know, they're not going to the same place. Okay, so it gets there. The minute I put these two together, they're going to love each other because this is kind of negative section and this guy is a positive section, and they're going to, boom, that's a magnet that they're going to attract each other. So I can put all the ones that I have that I no longer, I've already denatured my protein. Okay? I'm sorry? The minute I have this guy around, that's going to be a magnet and it's going to change the active site. Okay? Let's do problem 9 to see if we're really clear. Right, we'll get there before. Positive attracts negative. So heavy metal ions, you have a +2 ion. The minute you see a negative anywhere in this structure, you're going to have carboxylates, you're going to have negative ions in there that... Okay? So problem 9. Indicate whether the following describe a competitive or non-competitive enzyme inhibitor. Has a structure different from the substrate? What do you think? It's non-competitive, okay? Because in order for it to be competitive, both the substrate and the inhibitor have to have very, very similar shapes, structures. Competes with this substrate for the active site. Competitive. They're both going to the same place. Like us in the mall. We're all on that parking space. 9C. Addition of more substrate reverses the inhibition. Competitive. And you all answer, so we got it. Binds to the enzyme at the same time as the substrate. That's non-competitive and that's crazy. Addition of more substrate cannot reverse the inhibition. Non-competitive. Very good. Last page, guys. 271. Here we go. Enzymes and digestion. Okay, so digestion is a series of metabolic reactions that break down the foods that we ingest. And they break it down to smaller and smaller and smaller molecules by grinding, by softening, by mixing foods, and by catalyzing these reactions. Okay? The digestion begins in your mouth. So the minute you put a piece of bread, you're having a peanut butter sandwich. That bread is going to go in your mouth, and that polysaccharide that your starch is bringing is in your mouth. That very large, thousands of glucose units are going to begin to be cleaved. Okay? This is happening at a pH of around 7. This is salivary amylase, and it's a pH of 6.8, very close to 7. Okay, so your saliva has a pH of 6.8, and it needs to remain there. Then you are going to swallow it, and it's going to hit your stomach. Now, when it hits your stomach, the pH totally changes, 1.5. So salivary amylase that's coming with your sandwich, with your peanut butter sandwich, is going to denature. So you stop that reaction from happening. No longer amylase, no longer carbohydrates are going to be broken down, but another army of reactions are now happening because they are a totally different environment and a totally different pH. Okay, so we're taking a tour through your body. Now we are in the stomach. The salivary amylase is inactivated, it's denatured, and the pH changed dramatically, and now a totally different enzyme, pepsin, is activated. And now you begin to break down your proteins. So the peanut butter is going to begin to be broken down. Okay, so your protein begins to be broken down. And every time these hydrolysis reactions are happening, bonds are broken and energy is produced. ATPs are produced, which is what gets us to move, to breathe, to jump, to study, to walk, to dance, and to smile. By the same token, once you get to the pancreas, amylase, lipases, nucleases are produced. And a tremendous amount of reactions, and not only those, trypsin, carboxypeptidases, all of these come in. And small intestine comes in, and more reactions are taking place. In the small intestine, sucrase, lactase, maltase are breaking down sucrose, maltose. So you're already at the disaccharide level when you make it to the small intestines. Okay, so you had a huge starch molecule in your mouth, and now you're already at disaccharides. And the end products of the digestion of starch are, of course, monosaccharides, glucoses. Okay? And the protein is broken down all the way to what? To amino acids. So you go back to your monomers. And lipids are going to be broken down by lipases to what? To glycerol and what? And fatty acids. And then beta oxidation takes place, and every 2 carbons you cleave and you get more and more ATPs. So this is the whole cycle. We break it down, we get energy, we use it because we're moving and we're living and we're jumping around and dancing, and then we need more food to replenish more energy. Okay, if it ends in A's, what is it, baby? It's an enzyme. Okay, so look at the ending. And the endings, like when I did carbohydrates, everybody, of a lot of them, ended up in what? O's. And now we're doing enzymes. So if it ends in an A's, that's all you look at, the enzyme. And they're going to be huge words, but look at the enzyme. And if it ends in A's, it's going to be an enzyme. If it ends in O's, it's going to be a carbohydrate. These are glycerides. Okay, so you go from triglycerides to diglycerides to monoglycerides. Okay, so you break it down more and more and more, and now you're cleaving ester bonds. Any other questions? Congratulations, guys. We have done the entire course in 1033. Have a wonderful day, and I will see you next time.